everyone, I'm happy to present our work on ECCV 2024 called AdaNAT, Exploring Adaptive Policy for Token-Based Image Generation. Recent years have witnessed unprecedented growth in the field of AI-generated content. In computer vision, diffusion models have emerged as an effective approach. On the contrary, within the context of natural language processing, content is typically synthesized via the generation of discrete tokens using transformers. Inspired by such discrepancy, there has been a growing interest in investigating this token-based generation paradigm for visual synthesis. Different from diffusion models, these approaches utilize a discrete data format akin to language models. This basically includes two stages. At the first stage, a pre-trained VQ autoencoder is employed to perform the conversion between pixel space and VQ space. And at the second stage, a VQ space model is trained to perform generation at the discrete token space. In the direction of token-based visual generation, the recently proposed non-autoregressive transformers have exhibited noteworthy potential in terms of both generation quality and computational efficiency. NAS can generate images in just 4 to 8 steps due to their parallel decoding mechanism, which allows multiple tokens to be decoded simultaneously. However, this also includes challenges in determining the number of tokens per step, sampling temperatures, and other hyperparameters, leading to complex generation policies. While existing methods attempt to simplify this with scheduling functions, they require a lot of expertise. Meanwhile, a one-size-fits-all scheduling rule may fail to flexibly adapt to the diverse characteristics of different individual sample. Therefore, instead of employing a predefined static set of scheduling functions, in this paper, we consider a learnable policy network that automatically configures the policy network adaptively conditioned on each sample. This enables us to obtain a better generation policy automatically. Meanwhile, this policy is also adaptively tailored for each individual sample. However, to implement our idea, a non-trivial challenge lies in the non-differentiable nature of the discrete tokens and token-based generation process. Hence, we propose to formulate the policy network as an RL agent, which observes the states of generation, adaptively configures the policy to maximize generation quality, and can be trained through reinforcement learning algorithms like policy grading. The second challenge in implementing our idea lies in the reward hacking problem. And so specifically, we first consider two off-the-shelf design choices. First is the standard evaluation metrics like FID, and the second is the pre-trained image reward models like image reward. However, we found that with these designs, although the expected value of rewards can be successfully maximized, our resulting generative model usually fails to produce sufficiently high quality or diverse images. In other words, the policy network tends to overfit these rewards. Inspired by this phenomena, we hypothesize that it might be a rescue to consider a reward that is updated concurrently with the policy network during the learning process and adjusted dynamically under the goal of resisting overfitting. Therefore, we propose the adversarial reward model, which is formulated as a discriminator similar to that used in generative adversarial networks. When the policy network learns to maximize the reward, we refine the reward model simultaneously to better distinguish between the real and generated samples. In this way, the policy network is effectively prevented from overfitting a static objective, and we observe a balanced diversity and fidelity of the generated images. Experimental results on class-conditional image generation demonstrate that AdaNAT is able to outperform state-of-the-art diffusion models under efficient generation scenarios with 2 to 3 times less computational cost. For text-to-image generation, AdaNAT is highly effective as well. The ablation study demonstrates that both making the generation policy of NAT learnable and adaptive helps improve the generation quality. And the optimization process of the AdaNAT also clearly reveals the progressive improvement of the generation image quality. Finally, the visualization results of AdaNAT demonstrate that our method is able to achieve both high image quality and diversity. That's all for my presentation. Thanks for your time.